Ready? On the computer.
Microphone on.
Yeah, and it picks it up. All right. All right. So today we're covering Hess's law. So that's the second half of this unit. Chapter 9, Craig. Chapter 9 is all about those three formulas and putting them together. You've got a review sheet. That's to prepare you for your quiz on Friday, right? This is how you calculate that delta H. So in the equation, N delta H, okay, now I switch to that, do I? And I go, no, see, that's not doing it for me, that one. Delta, see? Oh, forget it. Okay, so how do I go back then? Okay, so in the equation, delta H equals N delta H, you were always given one of the delta H's, or you had to find it from Q equals MC delta T bit, right? But this is another way of finding delta H, and it's called Hess's law. Okay? So Hess's law gives us an idea of how to find delta H. He said that if you can't undergo the pathway directly, you can get there indirectly. Okay, that makes sense. If I can't go over top of the mountain, I can go around the mountain and to the other side. That's what he's saying. So if there's a reaction that you can't undergo in such, say, like a bomb calorimeter, okay, let's say it doesn't burn. So I can't undergo this reaction in the bomb calorimeter. I could actually undergo different reactions in the bomb calorimeter, add those reactions up together, and find out the energy from that first reaction. It's gone again. Okay, so, do you know what? This is so much easier if it's just a PowerPoint and a whiteboard marker. Okay, I want you first to understand this. What's this reaction? What's this equation? Do you recognize it? Photosynthesis? Photosynthesis? And the delta H value tells you? Delta H value tells you? Exothermic or endothermic? Endothermic. Is that true? Photosynthesis? Photosynthesis takes energies in, takes energy in, right? Light energy. And where's that energy stored? In the chloroplast, but in specifically which chemical? Glucose. In those bonds. In those bonds. So it takes sunlight energy and stores them as chemical bond energy. Okay? And then what happens with your glucose? You eat it, right? And undergo what? Come on, do you guys not know this stuff? You gotta know it for Chem 30. So what do we do with the glucose? We eat it, or the cow eats it, we eat the cow, whatever. But anyway, the glucose, and we react it with oxygen, and we produce CO2 and H2O. Unbalanced, I need a 6 there, I need a 6 there, and I need a 6 there. And what do you notice about this cellular respiration equation and the photosynthesis equation? They are opposite of each other, right? Okay? And so what will the delta H be? If I need, in order for photosynthesis to happen, if I need the sun to give the leaf 2,000 kilojoules per mole, what do you think you get out of photosynthesis?
2,000. You get energy.
How much energy?
2,000. Negative.
Right. I would get out 2,802.5 kilojoules per mole, burning 1 mole of glucose. And that's putting out, so now it's exothermic. So flipping the reaction, some reactions can be flipped, like this one, you know, photosynthesis to glucose can be flipped, and then that means that the delta H value is flipped as well. Okay? And something that the exam board loves to do is put in these biology applications. Okay? So there's one. You'll find another one about blood and buffers at the end of the season, and there's a few that'll come up. Okay, so they love talking about this because it's a reversible reaction that you should know from Chem 20. You should know that that's called glucose, or not Chem 20, I mean Science 10. And you should know that, therefore, then now the new lesson is that the delta H is reversed. Okay, so that's the first thing I kind of had to hit home. See if I push this and I push this. Yes, before we get into Hess's law. So there's two ways of calculating Hess's law. Today we're going to cover the first way, which is called algebraically. So Hess's law states that the energy of a whole reaction is equivalent to the sum of its steps. So the energy of the whole reaction, oh dear, see, push that one. The energy of the whole, oh dear, that one again. The energy of a whole reaction, A plus B giving you C plus D, is the sum of its steps. So I could go this way, get a little bit of E and F. I could take E and F and react them and go back to A and C. And as long as I add up 1 and 2, I should get this. Okay? Not as in distance. Don't be thinking distance. Think pathway. I can get to the same pathway. The energy going up this mountain and down this mountain, perhaps, would be the same amount of energy that I would need to go along this valley, through this, so across that, because it's a 2-day trek now. Okay, so I guess if you think of energy going up a mountain and down a mountain, it'd be about the same. Okay, push this. Push this. Okay, for example, if I were to take in my bomb calorimeter a lump of coal, carbon, diamond even, and I were to burn it and get carbon dioxide, I wouldn't get carbon dioxide. This is what you should get, right? If you say the combustion of carbon, you would have all put carbon dioxide, I would hope. But actually, in reality, you don't get carbon dioxide. You get a mixture, mostly carbon monoxide. So this is the problem. I can't do this in my bomb calorimeter, but I still want to write this in the data booklet. How much energy is released for this? So the book tells us that we can do it in 2 steps. My carbon and oxygen can react together and give me carbon monoxide. I can do that in my bomb calorimeter, and I can see the delta H of that reaction is exothermic 110. I can also do this. I can add more oxygen to my carbon monoxide. This is a bit tricky to think about because they're both gases, but anyway, it happens. And get my carbon dioxide. And that energy is 283. Okay? So, in that value, and if Colton, if you guys could hang out for just 2 more seconds, this is like the summary really. If I add these 2 things algebraically, and I see if I put carbon and oxygen and carbon monoxide and another half an oxygen and I add those together, I get
junior class change.
I get carbon, carbon, carbon from this carbon, carbon monoxide from that carbon monoxide, and one oxygen all on the left-hand side of the arrow. You see that? And on the right-hand side of the arrow, I have a carbon monoxide, carbon monoxide, carbon dioxide, carbon dioxide. And then like algebra, what's on the left, what's on the right, if I've put it in and it's still there when I get it, it didn't really participate, it's like a spectator ion. Remember canceling those out in Chem 20. This is the same idea that there's the carbon monoxides can be canceled out. And what am I left with? I'll go back to the blank screen. What am I left with?
C plus O2 C.
Which is what I was trying to find. And if I take these delta H's and I add them, I get this total delta H value, which is then the delta H value that belongs with this reaction. So negative 100 plus negative 200 gives me negative 300. You get that? Okay, the next step is more complicated. So Craig and Rob have a look on the book. Okay? Edson, and take your back. Okay, any questions so far? Okay, so Hess's law allows us to add the equations. We add the reactants and products and delta H values. We can always show these steps added together via an enthalpy diagram. What's an enthalpy diagram again? Good. Okay, harder example. So that was quite straightforward, I hope, and quite easy. This is where it gets harder. You may need to manipulate the equations. Can you read that back there? Okay. You may need to manipulate these equations further. So let's say we're doing this reaction. You're taking iron, you are combusting it. Gosh, that's going to be hard. Burning iron, right? So that's why we need to go about this Hess's law way, not a normal bomb calorimeter kind of way. So iron reacting with oxygen and getting iron 3 oxide. Okay, and I'd like to know what the delta H value for this is. So the question will give you 2 reactions, these 2. Okay, you don't have to make those up, they're given to you. So there they are, and they say, what is delta H of that? Okay, now, the problem with this red reaction is that my iron 2 oxide is on the left of the arrow, and what I want for my final answer is I want it on the right of the arrow. So just like the photosynthesis versus cellular respiration, we flip the entire reaction, and all we have to do is then flip the sign on the delta H. Okay? So one of the things you might have to do is flip. So you look for flips. So I want Fe2O3 on the right. So I flip the reaction. There should be a plus sign in there, no plus sign in there. That's my bad copy pasting. Gives you that. Okay? So ignore that plus sign, and there should be a plus in there. Okay. Do you see how that is the same as the above equation, as this equation? Just flipped. You see that? So iron, carbon dioxide, iron, carbon dioxide, iron 3 chloroxide, and carbon monoxide, iron 3 oxide, and carbon monoxide. Okay? And the delta H value is the same, just the sign is now reversed, in inverse. Everybody agree with that? Do you know why I flipped it? Why did I flip it? Raj? Why did I choose to flip this? Andy? No, why did I flip this entire equation? Why did I say, oh, I'm going to need to flip this one?
Because you need iron on the right side of the product.
Right, because I need iron 3 oxide to be a product. And at the moment it's a reactant. So I have to flip it. Okay? That's probably one of the hardest things to figure out. Because I'll say flip it, and you'll be like, well, how am I supposed to know that on my own? Okay, so I flipped it, flip the sign. Then multiply. Sometimes you have to multiply. So that's the other hang up you might have. Do you see how on my original equation, I think I push that button. On the original equation I have, on this equation that I flipped, I have 3 carbon dioxides. Right? And in my ultimate black thing I'm going for, I don't have any carbon dioxides. So I'm going to want all 3 of those to cancel out at some point. Right? If I use this equation, I only have 1 carbon dioxide that would cancel out. So actually I want 3 to cancel out, so I'm going to take 3 of these entire reactions. Okay, so I'm going to take that equation. I need 3 of them so that the carbon dioxides will cancel and the carbon monoxides will cancel, and it all works out. And so if I take 3, that's 3 times carbon monoxide, oopsies, 3 times the carbon monoxides, 3 times a half oxygen is 1.5 oxygens, 3 times 1 carbon dioxide is, well, 3 carbon dioxides. And now this goes back to the, remember per mole? This was per mole, and now I've got per 3 moles. So now I have 3 times that. So I had negative 200, now I have negative 800.
You'll have to go the other way, like divide at times.
I might have to divide sometimes, yeah. I could divide. They never really give that to you, but it is, yeah, absolutely possible. Okay, and now I'm anticipating that the carbon dioxides, carbon monoxides are going to cancel out. And I'll have my iron on the correct side and my iron oxide on the correct side. So there's the red bit, which I had flipped. There's the blue bit, which I had multiplied by 3. And if I add them together, I can see 3 carbon monoxides and 3 carbon monoxides cancelling out. I can see 3 carbon dioxides and 3 carbon dioxides cancelling out. And nothing else cancels out. So I'm going to carry the rest down. And I get my 2 irons carried down. I've done it in purple because it's a combination, right? Did it? Red and blue combination. My 1.5 oxygens carry down, and my iron oxide carries down. Which is kind of handy, because remember this original one that we used to flip over with the iron and iron 3 oxide? Didn't have any oxygen in it. So not only did the second equation help us cancel, it gave us our oxygen as well. And then I add the flipped version, the multiplied by 3 version, and I get my final version. It happens to be negative, so therefore it's exothermic. So this energy took some in, or this reaction took some energy in, this reaction gave out a lot of energy, and therefore the difference is exothermic overall, because there's more exothermic than endothermic. So you need to remember to, and remember to add states. What are the states on the iron? What is the state on iron? Solid, oxygen, gas, and iron 3 oxide. Solid. How do you know it's solid? First of all, it's an ionic compound. So unless it's dissolved in water, it'll be solid. Second of all, iron 3 oxide is rust. Solid. Okay. So look for flips, then look for multiplies, and then add everything together, like in algebra. Okay? It takes some practice, but that's all it is. This is as hard as it gets, this iron example. It's as hard as it gets. I could have 3 equations. Sometimes I need 3 to do my multiplying, flipping, whatever, canceling out. But that's as hard as it gets. Okay? So next you have a sheet. Looks like a little like this. We're just going to work our way through the sheet for the rest of the day to help us understand this concept. Okay?
And this isn't going to be on the quiz.
This is not on the quiz. The quiz is just chapter 9.